Welcome back. So, before the break we derived these two relations which are there on your slide. We derived expressions for the matrix elements in the initial and the final states of time ordered products of operators. Obviously, again this can be generalized to more than two operators. We worked it out for two operators. It can be generalized to n number of operators. Now, there is a further simplification that can be done in the case of quadratic velocity dependent Hamiltonian. If the Hamiltonian is quadratic in the velocity, as we did in the case of the transition amplitude, process is exactly the same. The path integrals over the momentum space turn out to be Gaussian in this particular case when there is a quadratic velocity dependence, and they can be evaluated explicitly, and we are left with expressions in the configuration space. As seen in the green box, the Gaussian integrals are captured by the normalization factor n script here, and the rest of it is of course to be evaluated in configuration space. The momentum integrals become Gaussian when there is a quadratic velocity dependent Hamiltonian, and it can be explicitly evaluated. It can be extracted as a normalization factor, and the rest becomes simpler to manage. Now, we look at the ground state expectation value of time ordered product. This is a 2-point function, and we want to work out the expression which is given on the right hand side. 0 represent the ground state, and the T operator is the time ordering operator which I mentioned before the break, and QT1 and QT2 are coordinate operators at time t1 and time t2 respectively. Right. So, we want to work out this expression which is given in your slide. What we do is we start with the coordinate space path integral, which is integral for this expression in the initial and final states, which the expression for the matrix elements. We start with that, and that is given by this in the particular case of quadratic velocity dependence. It is given by the expression which is in the bottom equation of your slide. Now, for the purpose of further development of this problem, we develop the expressions for the complete set of energy eigenstates and the representation of the wave functions in those bases. The eigenstates are defined by the eigenstates of the Hamiltonian operators. The energy eigenstates are defined by the eigenstates of the Hamiltonian operator, and they are numbered by the respective energy levels. En is the energy level, and the corresponding eigenstate is represented by the ket n. We are working in the Schrodinger picture. The subscript s represents the fact that we are working in the Schrodinger picture. So, the Hamiltonian acting on the energy eigenstates produces the energy eigenvalue and the energy eigenstates. Let us work out the moving bases. Q dash T dash, the ket Q dash T dash can be expressed in terms of the evolution operator, which is given in the square bracket, acting on the state coordinate state at t equal to 0. This is this Schrodinger state at t equal to 0, and this is the state at time t dash. As you know, in the Schrodinger picture, the states are time dependent, and the states evolve with time, and therefore, that is precisely what is happening. We are moving from the state at t equal to 0 to the state at q dash t dash by the explicit action of the evolution operator. Now, we introduce in the second step, we introduce the complete set of energy eigenstates, which is represented by this expression, and this one further simplification and the identification of the this product, this dot product as the wave function at q dash corresponding to the energy level n. Psi subscript n q dash is the eigenfunction or wave function at q dash corresponding to energy level n belonging to the state n. Right. So, this is where we were in the last slide. The first equation was where we concluded the last slide. Now, we insert two complete set of energy eigenstates. As the first one is shown in the blue box, they are both of them are shown in the blue box. The first one is numbered by identified by n dash priming, and the second by a double priming. So, these are two energy complete sets of energy eigenstates which are inserted as per the boxes given in this equation, blue boxes given in this equation. Now, what happens is that these eigenstates in terms of the expression that we had in the first expression that we have, the top equation, in terms of the top equation we can write this, let us call it equation 1 and let us call it equation 2. In terms of equation 1 we can write equation 2 in the form of equation 3. We have simply used the expressions for q dash t dash of equation 1 and simplified the expression for of equation 2 to get equation 3. There is no other change here, simply using equation 1 for q dash t dash and q double dash t double dash as well, both of them, and simplifying them and putting them substituting the kets q dash t dash and the dual q double dash t double dash by the respective expressions on the right hand side in equation 3, we get this equation 3. Right. So, the expression that we have from above is our first equation. Now, the important thing is, if you look at this carefully, what we want is the expression in this expression, we want this expression, but with the condition that n dash equal to n double dash equal to 0. Both the states n dash and n double dash should be the ground state. That is what we are looking at. So, we want to extract this this expression with in n dash and n double dash being 0, that is we want to extract this expression for the ground state. That is the objective. From this expression we have to evolve a mechanism by which we can extract the ground state expectation values. Now, let us look at this some basic behavioral patterns of the functions involved. If you look at the exponential minus I upon h e t or e n subscript n double dash t double dash as t double dash tends to infinity, this is clearly this expression of itself is oscillatory. This represents an oscillatory function in the as t double dash tends to infinity. It has a undamped oscillatory behavior because it is of the form exponential minus I infinity. As t double dash tends to infinity, this tends to exponential minus I infinity, which has undamped oscillatory behavior. Similarly, for the other exponential I upon h n e n dash t dash in the limit t tends to minus infinity, that would also exhibit similar behavior. So, how do we simplify it, or how do we extract the ground state from the expression that I mentioned here? From this expression, let us call it say equation A, we need to extract the ground state expectation value of t q t1 q t2, right. So, we do that by invoking the concept of regularization, as I mentioned some time back, followed by an analytic continuation. What we do is we introduce a damping factor. You would recall that what I mentioned just now is that this expression in the limit that t tends to infinity is undamped oscillatory behavior, and therefore, is problematic in computing its integral, and as such what we do is we introduce a damping factor so that it converges in a sense, and at least in the limit t tends to infinity it tends to converge. What we do, how do we introduce a damping factor? We introduce these substitutions. T double dash goes to tau double dash exponential minus I delta. Now, this is a damping factor, as you will see just now, this is a damping factor, and T dash goes to tau dash exponential minus I delta. This gradually eats into the oscillations, and as the time approaches infinity or time increases, and the integrals become convergent. Tau double dash, therefore, tau double dash can be written as exponential I delta into infinity in the limit that t tends to infinity. What happens? Tau double dash tends to exponential I delta into infinity, because this goes to the left hand side, it becomes exponential I delta t double dash tending to infinity means tau double dash tending to exponential I delta infinity, and similarly for the other case, for the case of t dash. Now look at this carefully. Exponential minus I delta can be written as cos delta minus I sin delta. Therefore, t double dash going to tau double dash exponential minus I delta. This is an explanation of how the damping effect is precipitated. So, t double dash is substituted by tau double dash exponential minus I delta, and this can be written in this form by substituting the expression for exponential minus I delta. So, exponential of minus I upon h e n dash t n double dash t double dash becomes this whole expression, with t double dash being substituted by tau double dash bracket cos delta minus I sin delta. Now, the important thing arises. This I and the second term minus I give me a real term, and the other term, of course, the cos term remains imaginary, but we now have a real term to as a prefactor, exponential minus 1 upon h, 1 upon h, mind you, minus 1 upon h e n double dash tau double dash sin delta. Now, the first expression being real, it converges and it forces the whole integral to converge. Now, you can also view this substitution, which is here in the first expression, first line. You can also view this as a rotation by an angle of delta in the negative mathematical direction on in the complex plane. As you can see here, it is a clockwise rotation. Remember, we use clockwise rotation in the negative sense, and it is a clockwise rotation by an angle delta, which takes this real axis to the towards the imaginary axis. So, the damping effect or the damping factor can also be viewed as a rotation by the angle delta 0 less than delta less than pi in the complex plane, of course, and in the clockwise direction, in the negative direction. So, we are given this expression, we have made this substitution as t dash tends to infinity. So, tau double dash exponential minus I delta tends to infinity, or tau double dash tends to exponential I delta infinity. This implies, or here we make an important assumption, the concept of analytic continuation. Here we make the assumption that because this expression is tending to infinity, therefore, it should also hold that tau double dash also tends to infinity. This is where the concept of analytic continuation comes into play. From the imaginary tau tending to infinity, we are now assuming that tau double dash tends to infinity on the real real line or real numbers. So, what happens to the limits? Now, let us look at it very carefully. Remember, as you will see later, the limits are very relevant in our given problem. You will come to know in the next 1 or 2 slides, but they are very relevant. But for the moment, just keep track of the limits. It is very important. You see, we are now looking at, we basically want to obtain this expression in the limit t double dash tends to infinity, t dash tends to minus infinity. You will very soon you will realize that these represent, or these will give us the, this will enable us to extract the ground state from the expression that I talked about some time back. So, this is what we want, this is what we want. Now, obviously, because of the problems we had of the integrals being oscillatory, the exponentials being oscillatory, we could not directly put the limits and extract out the required factors. We adopt a indirect procedure. We first do regularization, and then we talk about analytic continuation. The second step involves the regularization, which is nothing but introducing a damping factor, or equivalently introducing a rotation in the complex plane in the negative direction, in the clockwise direction. Now, this amounts to, here we invoke the principle of analytic continuation, and we say that if this is so, if the blue box is correct, then the green box must be correct. That is what we are assuming by the analytic continuation. As I mentioned here, highlight here, the cardinal step is taken in the third line when we make the assumption, when we make the replacement of the limits from this and this to, we make the replacement from the limits tau double dash tends to exponential I delta infinity to tau double dash tends to infinity, and similarly for the lower limit. We move from the imaginary values, of the rotated time coordinate to real values. So, that is these are imaginary values because of exponential I delta being here. So, we assume that if this holds for imaginary values, it also holds for real values. That continuation from the imaginary values into the real values is where we make the analytic continuation. So, and when is this possible? This is only possible if the matrix elements that we are going to evaluate, that the expectation value is an analytic function of t and t dash. So, then this transition, this shift, or this assumption amounts to analytic continuation, as I mentioned. Now, as a result of the analytic continuation, what have we got now? We have got this situation. The matrix element that we wanted to obtain, now we can attribute a matrix element from, you see what we, let me explain this. This is a matrix element which is well defined, because we have simply made simple substitutions, right. Now, we assume that there exists a matrix element with the limit, let us go back a minute, with these limits, that is well defined, right, but that enables us to define this matrix element, same matrix element with these limits. You see, look at it, this is the same matrix element e to the power minus I delta tau double dash. What is this? This is nothing but t double dash. If you look at this expression, this is nothing but t double dash. You can look at it here. Here it is, t double dash is equal to tau double dash exponential minus I delta. So, these are the substitutions we had made. So, this is nothing but we writing t double dash in a tau double dash, but then we make this a particular assumption that our assumption was that t double dash tends to infinity. Now, that implied tau double dash infinity, that implied tau double dash tends to e to the power I delta infinity, but that we assume that implies that tau double dash tends to infinity. So, here we are having this analytic continuation. Now, certain clarifications. The particular value of delta that we have chosen, you see we never said that delta needs to be small or large or whatever. So, delta is free so long as it remains between 0 and pi. You can take any value of delta between 0 and pi. It is very common to select delta equal to pi by 2. If you select delta equal to pi by 2, then our substitution, original substitution becomes t double dash goes to minus I tau double dash and t dash goes to minus I tau dash, and the limits become tau double dash goes to I infinity and tau dash goes to minus I infinity, which by analytic continuation, remember we said tau double dash goes to infinity and tau dash goes to minus infinity. Now, this rotation of the, you see the real timeline into the imaginary timeline by an angle of pi by 2. See the real timeline of the horizontal line, it is being rotated by pi by 2 to the imaginary line, and it is in the clockwise direction. So, it becomes like this, and that is what is called a Wick rotation, and it is very frequently used when we talk about moving from Euclidean path integrals to integrals in Minkowski space. You will be encountering that. It is a very important methodology for handling path integrals, because you see the point is path integrals in Minkowski space have certain questions, issues of convergence, and therefore, the usual practice is to work out the path integrals in Euclidean space and then go back to Minkowski space by analytic continuation, like we have done just now using Wick rotation. So, this is the substitution that we did. Now, by doing this substitution, what do we have now? If we go back to where we started, then we have G T 1 T 2, this is the matrix element in the initial and final states, and when we simplify this expression, you get Q double dash here, and instead of using delta equal to pi by 2, we can write this as minus I tau dot t double dash as minus I tau double dash and t dash as minus I tau dash. So, that is expression is taken here, and we write this expression here also, substitute the expression for t double dash and t dash in the prefactor also. The I factor clubs with this I factor earlier, and I get a factor of 1 here. So, this is simply algebraic simplification. Now, the important thing, the thing that I mentioned earlier, that why we need to extract this states with t equal to or t double dash equal to infinity and t dash equal to minus infinity. The important point is that the sum that we have talked about, the sum that we have talked about just now, this on the previous slide, this particular sum, as time passes, the state that would remain, as time tends to infinity, as the time of evolution tends to infinity, the state would remain that would make the most dominant contribution in the situation. The state that would remain in the situation that makes the most dominant contribution when time tends to infinity would be the ground state, because ground state has the least energy. So, having the least energy, as a result of which, as time tends to infinity, the one state that will make the maximum contribution in the situation when in an infinite time has elapsed would be the ground state. Why? Because it has the lowest energy, and therefore, its fall off the fall off rate of this ground state is the least, because it has the lowest energy. So, naturally the fall off rate or the loss of energy from the ground state would be the least, and therefore, when you take the limit as t tending to infinity, the state that remains is nothing but the ground state. So, in other words, what we want to extract from this is the ground state. In other words, as I take the limit tau double dash tending to infinity, tau dash tending to infinity, what I get is what I want, that is exponential minus I 0, this expression, from which I can clearly extract out this particular factor. This is what is required, the expectation value of the time ordered product of operators q t1 q t2. So, my problem is now to take the limits or to get the limits in this situation that tau tends to infinity, tau double dash tends to infinity, I am sorry, and tau dash tends to minus infinity. So, this is what we had from above. So, no problem with that. And as far as the dotting of these two states are directly concerned without the matrix elements, we get this expression straight away, n double dash n dash, these two factors would not make their presence, would not make their appearance. Now, the important thing is we look at this expression. You look at this expression, we can simplify it considerably by invoking the orthonormality of the energy eigenstates, and the n double dash equal to n dash survives, the rest of the states go away, and we have the summation over n dash only, and the n double dash quantity simply goes away. Now, in the limit that tau dash tends to infinity, tau double dash tends to infinity, tau double dash tends to infinity, tau dash tends to minus infinity, what happens? We get this particular expression. This is the expression that we had for the ground state. Why? That is shown here. This expression amounts to the application of the Hamiltonian on this wave function, and that is simply this particular state. How? So, to repeat, how I have got the expression in the green box is shown by by the expressions in the blue box, right. Recall that E0 is the ground state eigenvalue of the Hamiltonian. So, that has been used in arriving at the ground state wave function. So, at the end of the day, what do I get in the limits that tau double dash tends to infinity, tau dash tends to minus infinity, I get this expression on the one side, this is equation 1, and I get this expression, this is equation number 2. Now, as you can see here, the prefactor of the quantity that I require, the prefactor of the quantity that this is the quantity that I require, the prefactor of this, that is this whole quantity, is nothing but this expression, which is nothing but this expression. So, let me repeat, the prefactor of the quantity that is required in equation 1 is the same as the quantity in equation 2. So, that enables us to isolate the quantity of interest and present it as the expression in the green box. So, now the last step is to do the analytic continuation back. Earlier we had the analytic continuation from with an angle of pi by 2 clockwise. Now, we revert pi by 2 counterclockwise, and using that we go back to our original variables t dash and t double dash, and write the integral as t double dash tending to infinity, t dash tending to minus infinity of this expression. So, and which in the path integral framework we arrive at as the expression in the green box. So, the expression in the green box, limit t double dash tending to infinity, t dash tending to minus infinity of the path integral numerator, path integral denominator. Numerator we have the additional quantities or the eigenvalues of the two operators, gives us the vacuum state expectation value of q1 and q2 time ordered. Thank you.